Good morning, AP Calculus AB, and welcome to your last lesson in Topic 5, Antiderivatives and Integration. This was a pretty hefty unit, really laying the foundation for the rest of the semester. We only have 2 units left, actually, to finish our content, and both of them are much, much shorter than this one. So thank you for slogging through and getting all the basics down. As you can see, our title for this is the average value quote theorem, end quote. It's not really a theorem, but it's so connected to a theorem that I always call it a theorem. And you'll see that further explained as we move through the lesson. Because it is connected to a theorem, I thought today would be a nice day to go through and remind you of our other theorems that you're expected to know. There are 4 other theorems that get called up fairly often. The IVT, the EVT, the MVT, and the Squeeze Theorem. Now, technically, there is the 5th and maybe most binding and important theorem, the fundamental theorem of calculus, but we use that so often that I find students don't forget that. So we're going to run through these 4 very quickly. We've actually done something like this before too, so why don't you take a quick second, fill in everything here, or fill in what you can, and then if you're feeling really bold, there is a nice little short free response at the bottom that uses 3 of those 4 theorems. So we'll give you some time, and then we'll come back together and see how you did. Ready, set, go. All right, and we're back. I'm going to just run through these pretty quickly. I think if you really want to go more in depth, just find the videos that are actually about these theorems. This should be a review, not a full in-depth look. The full name of the IVT is the Intermediate Value Theorem. EVT is the Extreme Value Theorem. MVT, Mean Value Theorem. The Squeeze Theorem is the Squeeze Theorem. The criteria for use for each of them is actually kind of nice because most of them have the same criteria for use and then you add on to it. And what is that main criteria for use? Your function has to be continuous on a closed interval. And you do need to state that when you're referencing a theorem, right? We can use this because our function is continuous on that closed interval. And so I'll write that on all 3 of our blank VTs over here, and this will actually hold true for the AVT as well. Kind of. The MVT has one additional criteria because the mean value theorem will actually start at the end here. Because the mean value theorem is going to guarantee that if you find f of b minus f of a divided by b minus a, right? We've called this the average rate of change or the slope of the secant line or slope of the endpoints, whatever we're calling. So the mean value theorem says find that slope, and that's going to exist because this is continuous on a closed interval and there are endpoints. But the mean value theorem is going to guarantee that after you find the slope of the endpoints, they're going to say, cool, there's going to be some value c, where c is an element, right? C is some number between the endpoints. And you're like, well, cool, there's a number between the endpoints. What do you do with that? Well, you take that number, you find the derivative of f at that number, and they are saying that the derivative at that number will be equal to the slope of the endpoints. And we did this by showing that there would be a tangent line that is parallel to a secant line. They're the same value. And because we are guaranteeing that a slope is going to exist in between the endpoints, then our function also has to be differentiable, right? Differentiable is our fancy calculus way to say that there are slopes that exist at every point between the endpoints. And while we're here, what work do you have to show for the MVT? You need to show this. All right, we might as well tackle these other 2. The IVT, always hard to put into words, I think, what the IVT guarantees. So let's maybe start with the work. The work you're going to have to show is that you're going to have to find f of a, the output for one of the endpoints, and you're also going to have to find f of b. Technically, these can't be the same, because if they're the same, it's kind of a very boring problem, but doesn't really matter there. You're going to have to find the endpoints, and that's really the only work you need to show there too. But what they're going to guarantee is, and I always like to show a graph, I think visually it's a little bit easier here, right? If we have a and f of a, and b comma f of b, okay, they are just saying that if we look in between the outputs, there are, of course, a bunch of values there. Let's say that this output was like 2 and this one is 5. Well, then on our journey from the starting point to the ending point, the IVT is just telling us that it must pass through every output between 2 and 5. Right? There has to be a point somewhere on here that has an output of 3 and 4 and 4.7 and so on and so forth. Doesn't matter how you draw it, we have to pass through every number between 2 and 5. So normally set up on this problem will be something like, prove that there is a number that this function passes through the number 4. Well, you just find the two endpoints. I'm hoping that they're not equal. They won't be. And then you should also state something like, let's say that they're looking for 4. I don't know. You should also say that f of a or f of b, whichever one's the smallest, is less than 4, which in turn is less than f of b. So you should state those two before you write your conclusion. And that's that. What about that EVT? Well, you don't really need to do much with the EVT. I've only ever seen the EVT as a multiple choice option. I did make up a problem down below that shows it could be on a free response. We'll touch on that shortly, but what does the EVT guarantee? Well, the EVT guarantees, and let's pick two other numbers. Let's say we have points C and D, where C and D are, including the endpoints, some values in between A and B, possibly at A, possibly at B, where when you evaluate C in your function, that one single number is going to be less than every other number in the function. This we would call an absolute min. And in turn, if we evaluated our function at D, that would be greater than every other value in our function. Now, technically, they could all be equal. The absolute min and the absolute max could be the same number. That's a rare occasion, but it does happen, and they do expect you to know that. But again, the EVT just guarantees that there is going to be an absolutely largest value on a closed continuous interval and an absolutely smallest value. What work do you have to show? You might have to show that the function is continuous, but that's really about it. Again, this is mostly a how come there has to be something? Well, if it's continuous, there has to be something. Last but not least, I used to spend 0 minutes outside of the sixth lesson of the year on the Squeeze Theorem, but then a couple years ago they said, haha, there's a free response that has a Squeeze Theorem problem, and then I felt really bad. So now I try to keep that popping up every now and then so it stays fresh in your mind. What does the Squeeze Theorem actually do? Well, the Squeeze Theorem helps us find a limit, right? The Squeeze Theorem is going to guarantee that we're going to be able to find the value of a limit. I'm going to call this g of x. And I'm going to expand on that in just a bit. But in order to use the Squeeze Theorem, you first need 3 functions. You need f of x, you need g of x, and you need h of x. And g of x as a function is going to have to be between, think in the middle of f of x and h of x. Let's say f of x is smaller than g of x, and if h of x is greater. So they're going to give this to you somehow. They're going to say h of x is bigger and f of x is smaller. And there's one other thing you need as well. The other thing you have to know is that the limit as x approaches a of f of x of the bottom function is equal to the limit as x approaches a of h of x, the upper function. And honestly, what kind of work do you have to do? Sometimes you might have to show that. You might have to explain that's there. They'll usually tell you this fact. Okay. So then what does it guarantee? Well, it tells you if f is below and h is above, but their limits are equal, then it tells you that the limit of the middle function at that point A is equal to the other two limits. And that's it. Right? The Squeeze Theorem helps guarantee a limit value. Sometimes you'll see it used for the definition of continuity, but that's that. Alrighty, so if that helped jog your memory, maybe you can pause again and try these, but hopefully you already tried these, and we're going to run through right now. So they are giving us a friendly function over here, and they're telling us that our function is twice differentiable, and we give select values for f, right, that's right here, and also f prime from -1.5 to 1.5. Cool. A is there guaranteed to be a value a where a is somewhere in between or possibly including the endpoints, and f prime of a is a maximum? All right, well, let's see. We know we're using theorems, and they're asking about a maximum. Oh, I think this has got to be the EVT, right? So for the EVT, we need to take a look at f prime. That's this guy down here. And they're saying, is there guaranteed to be some value, not even necessarily the values in the table, it could be ones in between, where that value is bigger than all the other f prime values? And I think our answer here is probably yes, right? We do something like this. As f prime of x is continuous on, and I'm going to shorten the way they wrote it, 1.5 to 1.5 with a negative, right? Then the IVT, and then I'm going to be extremely lazy here, guarantees there to be a value a such that all of this and f prime of a is a maximum. Cool. Do a little star. Don't do that in the AP exam. Actually write that out. I think we should write that, but there are two things maybe to talk about. First, what if they wanted you to actually find the maximum value here? Well, jumping back up to the EVT, if they actually wanted you to find the maximum value, which is not the point of theorems. Theorems guarantee the existence, but if they wanted you to find it, you'd have to bring in the candidates test, right? You'd have to take the derivative of the function they're talking about, find your critical points, and then plug them all back into the original function. But that's not what they're asking for. The second issue here is that you would not receive full points for what we put, not because I was so lazy on the conclusion, but because you just stated that f prime is continuous. If there was a function, like if they said f prime is the function sine of x, then you could just say as f prime is continuous. If there was a graph that was clearly continuous, you could say as f prime is continuous. But there's a table over here. And my question to you would be, how do you know this is continuous? How do you know you don't just pick up your pencil and skip through individual dots here? Well, the key, of course, is in the original problem. They told us that f is a function that is twice differentiable. And that's a very, very common setup for these problems, but it's something we don't talk about very often, right? F being twice differentiable tells us a couple things. First, and I'm going to write this, and you do actually have to write something like this out. You can put it at the very beginning, and then it will apply to every problem. So I'm just going to use the space down here, and I'm going to say as f is twice differentiable, then f prime is differentiable. Twice differentiable means you can take the derivative of f and all those derivatives exist, which tells us that there's all the values of f prime, no DNEs. But twice differentiable means you can also take the derivative of f prime, so to get f double prime, and all those derivatives exist too. But more than exist, for a function to be differentiable, the function also must be continuous, because differentiable means the slopes or the derivatives exist, and for a derivative to exist, our function must be continuous. So as f prime, and I'm going to do both, and f are differentiable, then f prime and f are continuous. There we go. Now we've bridged the gap from differentiable to continuous, and let me tell you, you must write that sentence. I graded this last year, and it was 2020 of that year. I graded this in 2020, and there were several students that would have gotten a perfect score on the free response I graded, except they forgot that one sentence. Very, very uncommon, and I think a lot of students assumed, they're like, well, if it's differentiable, it is continuous. And you're right, but you needed to tell us that, right? How do we know you just didn't say, I don't know if it's continuous or not, but my teacher told me to write continuous, so I'm just writing it. So they do want to see that connection when you're justifying with the theorem. Once we've written that, then we're good to go on A. All right, let's go ahead and jump down to B. Is there guaranteed to be a value B, where B is between the endpoints, where f prime of B equals -1? Well, let's look at the f prime values again. Looking at the f prime values, we start at -7 and we end at +7, and we're continuous. So somehow we have to get from -7 to 7, and to do that, we have to cross through every y value in between those. -1 is in between. Okay, so this to me is our IVT. Let's get to it. We should show f of -1.5, which is -7, and we should also show f of 1.5, which is 7. Nice symmetry there. Okay, as f prime is continuous and f of negative 1.5 is less than, what are we talking about? Negative 1 here? F of negative 1.5 is smaller. Yeah, negative 1, which is less than f of 1.5. Then the Evt guarantees, good spelling practice, and then intense laziness again. There to be a value b such that blah, 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 blah. Great. Some students would say, well, wait, I can do better than that. Couldn't I know that negative 1 has to appear on the smaller interval? Sure. You could totally use negative 0.5 and 0 and then rewrite the inequality with those. Great. Nothing wrong with that. And in fact, in past years, they have actually asked on a smaller interval than what was guaranteed up above, and you can totally shrink down an interval and have all the properties still exist. Great. Well done. Last problem. Find a positive real number r having the property that there must exist a value c, oh my gosh, 2 extra variables, where c is in between 0 and 0.5, not including the endpoints, and f double prime of c equals r. Whew. Now I'm recognizing this setup as the mean value theorem just because I've done this many, many times. One of the giveaways is they're not including the endpoints, right? And when we don't include endpoints, very often we're talking about slopes. That's why we don't include the endpoints. You can't have slope at an endpoint. And the second giveaway is they're asking about f double prime of c. And I don't see, no pun intended, f double prime up here at all. But we can at least tell something about f double prime by taking the slope of f prime. Right? The slope of f prime is f double prime, right? So let's use our slope formula with f prime. In particular, let's find f prime of 0.5 minus f prime of 0 divided by 0.5 minus 0. Okay? F prime of 0.5 is 3, just from the table, minus 0 over 1/2. Then we can do 3 times the reciprocal of 1/2, which gets us 6. So what did we find here? We said if we're looking at the graph of f prime, right, here's our graph of f prime, and we're looking between 0 and 0.5. Okay, so we're at 0, 0, and 0.5, comma 3 up here. Who knows what the graph does in between? Maybe it goes blah, 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 blah. Doesn't matter. But they're saying we just found the slope between those 2 points. We found the slope of that blue line. And because this is the graph of f prime, what we found is the average rate of change, right, oftentimes abbreviated average rate of change of f prime. As soon as you see rate of change, then we're talking slope. So we just found the average slope of f prime, which has to do with f double prime, the derivative of f prime. So what can we guarantee here? As we're talking about f prime here, as f prime is continuous on 0 to 0.5, we showed that earlier, and differentiable on 0 to 0.5, showed that earlier. And you can actually use closed endpoints here if you want, because we talked about how it's differentiable everywhere. But either way, then the MVT, I won't be as lazy here, guarantees, and I'm going to start rewriting up above, guarantees there must exist a value c such that, common abbreviation, 0 is less than c, which is less than 0.5, where f double prime of c equals 6. We showed the work for 6 up here. Great. Tricky problem because they were very, very vague there, but it's a very common setup that they'll give you a function and they'll ask you about the derivative of the function, and we need to recognize the setup to the mean value theorem. All right, now you hopefully are looking through this and said, wow, we just spent an incredible amount of time on review, but it's not bad for you. The reason we did that is because today's lesson goes a little bit quickly, but it's very much related to our mean value theorem. In fact, we are going to start on the next page with the mean value theorem for integrals. The mean value theorem we just looked at is known as the mean value theorem for derivatives. This second mean value theorem is the same as the one we just did, but phrased so that it uses integrals instead of derivatives. And you're like, well, why? The reason why is because with derivatives, we can use the mean value theorem to guarantee a rate of change. If we apply this to integrals, then we can guarantee something about area. So there's two different ways to apply the mean value theorem. And luckily, coming up with the mean value theorem is not bad at all because we're just going to use the mean value theorem for derivatives. So let's begin. We know that this rate here finds the average rate of change. Now, I used the function capital F to find our average rate of change because that has a nice connection to our area function, to our integral. You could have used any function here. But either way, average rate of change, very commonly abbreviated like so. Now, what does it tell us? Well, it tells us that if you find the average rate of change of a function, then there is some value between a and b, which we usually call c, where if you plug that value into the derivative of this function, how do we show the derivative of capital F? Oh, it's lowercase f. If we evaluate c into lowercase f, it will be equal to the slope of the endpoints, the average rate of change, the slope of the secant line, whatever we're calling it. Now, if we wanted to convert this to using integrals, we might realize then that f of b minus f of a is actually the conclusion of the fundamental theorem of calculus. And so I could probably rewrite that using integration. I could say the integral from a to b of lowercase f of x dx. And hopefully, since we've done the fundamental theorem a few times over the last few days, or a lot of times, you can see that you would take the antiderivative, which becomes capital F, and then substitute in b, substitute in a, and we'd get that piece up above. Those two are equal to each other. Last but not least, for the fundamental theorem, or no, I'm sorry, for the mean value theorem for integrals, we're going to isolate that integral. And isolating isn't bad at all. We just need to remove that friendly denominator from over here. And so we end up with f of c times b minus a. This is known as the mean value theorem for integrals. However, we, pun intended, need to actually give this meaning. Now, some of it we already know. We know that the left side of the equation that I'm highlighting and attempting to highlight in purple over here, if my computer decides to cooperate, there we go. We know that that is going to measure, of course, the area between the curve and the x-axis. I mean, that's what our integral does. But what about the right side? Well, if I wanted to sketch a nice little graph over here, okay, and we're going from a to b, b minus a is just subtracting the two endpoints, and we've seen before that's going to give us the distance between a and b. So when we've used these distances before with respect to area, then we could probably think of that b minus a as one way, the length of the interval. However, another way is when we first started integration, we used this length as like the base of a rectangle. So maybe we could call this over here the base. Well, now we can put everything together pretty quickly. The integral measures area, and if the base is b minus a, then what could we take f of c to be if we know that these two sides are equal to each other? Well, hopefully you're saying, oh, then f of c probably represents the height. So this guy right here is going to be a height, because when you do a base times a height, it gives you an area, and these are equal. Now, what does this actually mean? Well, let's look at a picture. So the one in purple, and I'm going to use this function over here, just this small interval. This is purple, and the integral is measuring, of course, all of this shaded area between the curve and the x-axis, like so. All right, great. That is the purple piece, right? We see it up here. The yellow part, b minus a, is measuring the length of the base, and then f of c is a point, right? I'll do this in red. F of c is a point on the function f, and it doesn't have to be in the middle. I know my picture shows it in the middle, so I'm going to go with that, but I stole this off the internet, and thank you for whoever I stole it from. Is a point on here which helps us create the height of the rectangle. So the height of this rectangle is f of c. But there's one very, very, very important characteristic of this rectangle that we just drew right here. and that is that this rectangle, or the area of the rectangle, is equal to the area beneath the curve. So visually showing, that means that this rectangle right here, including this little empty gap over here that is included in the rectangle, that red area that I just drew in is the same area as the purple area. So if we wanted maybe a better explanation, if a curve is continuous on a closed interval and differentiable, because it's the mean value theorem, right? Then it's possible to draw a rectangle that has the exact same area as the area beneath the curve. And the rectangle is going to be created using a point on the curve. So this is the mean value theorem for integrals. It guarantees that using the same base as our integral, there's going to be a height where the area is the same. Now, this might seem completely unrelated. You're just talking about areas. How is this the same? Well, it's still using f of c, right? So there's two different ways to interpret that f of c. F of c is the height of this rectangle that makes the rectangle with the same area, but f of c is still over here, right? F of c is still the derivative that matches the slope of the endpoints. And so if you take a look at the slope of the endpoints over here, right? Here are my two endpoints, and we look at this line like so. That was a terrible line, but you won't judge me too much. Then if, and this is a tough picture to see, mostly because my drawing was terrible, this second line that's supposed to be tangent to my graph that looks, I don't know, how's my tangent line going to go? Something like this, I guess. That is still supposed to be parallel to this line over here, right? So it is still the mean value theorem. It's just a different way to look at the mean value theorem. So you can either think of this f of c as the same slope as the endpoints, or f of c is the point that allows you to draw a perfect rectangle that has the same area. Okay, so we're going to go ahead and try one of these. I will tell you that the mean value theorem for integrals I don't think has ever been asked on the AP exam, but we are going to manipulate this result into something that is asked every year, and I think it's a nice little practice problem. So, find the value or values of c guaranteed by the mean value theorem for integrals for the following function over the interval 1 to 3. Well, ultimately, and I'll kind of show this over on, we'll split this maybe into thirds, I think. Ultimately, we are going to need to show that the area from 1 to 3 beneath the function of 9 over x cubed dx is equal to some value of c, or f of c, times b minus a. So there are a few things we need to do here. If we want to determine what c is, we first need to find the area, and I'm going to do the work for the area over on this left side. So to find the area, we can probably factor out the 9, integral from 1 to 3, and then rewrite x cubed as x to the negative third, right? Yeah, that looks pretty good. And then we can keep the 9 to the outside, find the antiderivative, so add 1 to the power, negative 1/2 to cancel that out from 1 to 3. Keep the 9 on the outside. And actually, let's have the negative 1/2 join it as well. So negative 9/2. And then x to the negative second, 1 over x squared from 1 to 3. And then negative 9/2. Substituting everything in, 3 squared is 9 minus 1 over 1. Common denominators, negative 9/2. 1/9 minus 9 over 9. So negative 9/2, good thing I used a lot of room here. This is negative 8/9. Oh, whew, everything cancels here. Look at this. The 9s go. Okay, these become a positive. And then we can cross reduce these to become 4. So I think we're just getting a final area of 4. So the area beneath the graph of 9 divided by x cubed is 4. Whew, came out to be a nice number. I was a little worried there. All right, so what have we done? Well, this is 4. This is f of c, and then this guy is, of course, 2. Well, it seems like we could isolate f of c. So if we divide 4 by 2, we get 2. So this tells us then that the height of the rectangle is going to be 2. So visually what we've done right now is we've said, okay, we're going from 1 to 3. There's some curvy curve over here. and we know that the length of the bottom of the rectangle is 2, and they're telling us the height is going to be f of c, which equals 2, right? I mean, 2 times 2 is clearly going to match the 4, but there's one thing we haven't done. We don't know where on the x-axis we can draw up to the function and have a height of 2. We don't know the x value. We don't know the input. But that's okay because we know the output. If the output is 2, then we'll jump over here. If the output is 2 and we're looking for a value c, then aren't we saying that we want to know when 9 over c cubed equals 2, right? We want the input. So we multiply both sides by c cubed, divide by 2, and then finish off by taking our cube root. So what is this telling us? It's telling us that if we go to the cube root of 9/2, I don't know what that is. I bet it's somewhere between 1 and 3 though, right? So let's say that this is the cube root of 9/2. Oh, that was somewhat terrible. Let's say that this is the cube root of 9/2. Then when you draw up to your function, this is going to be at a height of 2, and that will let us create a rectangle that has the same area as the area beneath the function. Or more visually, I have this prepared on Desmos for you. I figured you guys could enjoy the visual here. The mean value theorem for integrals. Here is our graph, and we can see that the area below the graph, so I restricted it, so it's just this little sliver of a piece in here, has an area of 4. Here is the base, right, from 1 to 3, and then here is the height, right? So this is where the cube root of 9/2 is, and we drew up to the graph, and then the rectangle would be outlining along the green portion with a height of the purple, and that rectangle, or in this case actually a square I think, would have the same area as beneath the curve. Great. There is our mean value theorem for integrals, but I mentioned that we were going to use this result to help us find something else. So let's do a temporary sidetrack, and then we will come back together. So what is this temporary sidetrack? Well, the temporary sidetrack has to do with a different, completely unrelated equation. So we have the equation f of x equals cosine of x. Right? And I'm going to go ahead and actually sketch a quick graph of this. We're just going to be looking for cosine from 0 to pi over 2. Okay, we should know that when you do cosine of 0, you get an output of 1. We should also know when you do cosine of pi over 2, cosine of pi over 2 is 0. And then it kind of curves something like that. Okay? So we're going to be looking just at this portion of cosine. And my question is, what is the average output on this interval? And that's kind of a weird question to wrap your head around, the average output. But you can see that there are many different outputs on here. I mean, one output was 1, one output was 0. If you substitute in pi over 4, right, we know that one. The cosine of pi over 4 is root 2 over 2. But what is the average? What is the, and it's tough to say the output in the middle because that's not quite how averages work, but either way, what is the average output? So maybe one way you could think of an average output is like you think of means, right? If you're asked to find the mean of a few numbers, what do? Well, you add up those couple of numbers, and then you divide by however many are there. So let's close this one out. I have the same graph here again. I'm going to zoom a bunch in here. And I'm also going to go ahead and rework our axis. I think we'll go in terms of pi. So let's go negative 2 pi to 2 pi. And let's have it go by like pi over 4s. There we go. Okay. So we can see this guy right here a little bit more clearly. There's that same piece of cosine. And so let's say that we wanted to find just the average of two values we know on here. In particular, let's say that we want the average of this output and this one. The outputs are 1 and 0. So how do we find the average? Well, I was very lazy and used function notation. I said g of 0, which is the first output, and g of pi over 2, which is the last one. There are two that we're adding together, so I divided by 2 and said, okay, the average, if you just use 2 data points, is 0.5. But there are certainly more than 2 outputs on here. So we could maybe, let's do that one where I said pi over 4, right? And the order doesn't matter, but I'll try to keep the order going. So we add those 3 together, g of pi over 4, which is root 2 over 2. So now I've added this guy, and this one together, so we need to divide by 3. And when I use 3 data points, we get 0.569. So a little bit bigger than 0.5. We can add others too, right? I think maybe we can see that pi over 8 will be on that interval, so g of pi over 8. Okay, there's 4 of them. Now we get 0.65. Let's add another, let's see, 0 pi over 8, 1 pi over 8, 2 pi over 8, 3 pi over 8, I think we could do too. G of 3 pi over 8. Now there's 5 of them adding up, so we need to divide by 5, so we got 0.602. And you could continue the same process, right? I essentially split this into 4 subintervals, 0, pi over 8, 2 pi over 8, 3 pi over 8, 4 pi over 8, and then added up all those divided by 5. Now, how could you be more accurate? Well, if you want the average output, wouldn't you technically have to add up every single output here? And there's an infinite number of outputs, so that might take you a while. Well, you might say, well, to get a really good approximation, couldn't we continue the same process here where we go through and we just split it into smaller and smaller subintervals? Maybe I do pi over 16s next, or pi over 32s, and start dividing by something like that. And the answer is sure. In fact, that's how you could really find a very, very good approximation. And so summarizing what we're doing right there then, since there are an infinite number of outputs, there we go, since there are an infinite number of outputs, okay, then we would probably want to subdivide this interval into smaller and smaller pieces, right? We'd find all of those outputs. Maybe you'd say sum up by all of those outputs. And then we'd divide by the total number of data points, or maybe you could think of the total number of subintervals. Okay. Now we would do smaller and smaller subintervals, and eventually you'd want to do infinitely small subintervals, which I think we've seen before, right? If we said n is the number of subintervals, we'd let n tend to infinity, right? We'd let n go to infinity. Maybe we'd even write it as a limit. Yeah, I think we've seen something like that. And then if that's a limit and we're summing all of these data points up, then what does that relate to? Oh yeah, that actually relates to integrals. Isn't that what an integral does? The integral says we're going to have dx, which is something infinitely small like our subintervals, and then we're going to sum a whole bunch of things up. Well, let's conclude here. You don't actually need the mean value theorem for integrals on the AP exam, to my knowledge. It might be in the course description, which means it could show up on the exam, but I've never seen it. You do, however, need what's known as its corollary, something connected to it. And it turns out that that same f of c value, oh my gosh, that f of c is just everywhere, isn't it? The one that allows us to draw the perfect rectangle, the one that is the average rate of change, is also the average value of the function. If you want to check out the proof, I gave you a link on here. It's actually a very straightforward proof, and he does essentially the same thing that I was doing up above, except he shows how to take it out to an infinite number of data points to find a better average. Now, if f of c is the average value of our function, let's go ahead and rearrange our function to isolate f of c, because that's what we're interested in. Now, to do that, you could divide by b minus a. So there's nothing wrong with saying the average value is given as the integral from a to b of f of x dx divided by b minus a. But I see it much more commonly written as 1 over b minus a times the integral from a to b of f of x dx. Hopefully you can convince yourself that these two are the same. And sometimes people will say, well, wait, how do we show that this is the average value? I've seen a couple ways. Maybe the most common is they'll put a little bar over the top, right? That bar notation, you may have even taken a stats class where they call this x bar, or maybe you saw this in geometry, where x bar is very commonly defined as the mean, right? If they say find x bar, they mean add up all the numbers and divide by the number of numbers there. I've also seen some people write this as f sub average, right? And it's not sub-average, I'm just saying sub because it's a subscript. So either one of those are fine, or you could just write the average value is, and then, go from there. And so this really brings us to our last quote theorem, end quote, which is the average value theorem. And as a nice reminder, this isn't really a theorem. This is more a formula, right? It's a formula that you do need to memorize. You need to realize that finds you the average of the value of the function that's right there. And sometimes people can get confused and they're like, wait, how does that have to do with lowercase? Because you're going to do the integral and that brings it to uppercase. Well, it does, but if I extend this out a bit, right, it's going to definitely give us f of b minus f of a, capital F. But then because we're dividing by the b minus a that's over here, isn't this actually the slope of capital F, right? This is the slope formula. And so when you find the slope, it brings us back down to lowercase f. So yeah, it's kind of weird. It takes the antiderivative and then kind of like takes the derivative again. So it brings us to capital F and then brings us back down to lowercase f. But either way, back on that theorem stuff, because it relates to the mean value theorem for integrals, it is the mean value theorem for integrals. It really has those same things where the function needs to be continuous and differentiable on the open interval, just like the mean value theorem, but they never ask you for that, so that's kind of a blessing. It's just find the average value. But I call it the average value theorem because it just seems, I don't know, fitting, the AVT, right? So let's try this. What is the average value of cosine of x on the interval from 0 to pi over 2? Okay, well, average value is given by 1 divided by b minus a times the integral from a to b of cosine of x dx. This will tell us the average output on the graph of cosine of x. So 1 over pi over 2 times, now we have the integral to do. Antiderivative of cosine is a nice one. It's just sine. Derivative of sine is positive cosine to check your work. Continuing out, 1 divided by a fraction is always the reciprocal of that fraction. And then working this piece, we have sine of pi over 2. We'll pretend that's a 2. Minus sine of 0. Okay, sine of 0 is 0. Sine of pi over 2 is 1. So 1 times 2 over pi is 2 divided by pi. The average value on cosine is 2 divided by pi. Think of pi, we can go engineering status. Think of pi as approximately 3. 2 divided by 3, 0.666, somewhere around 0.666. And we were honestly approaching that on our graph, right? When we had added up 5 values, we got 0.6 something. So not too much of a shock, though. So yeah, the average value, if you were able to add up all the values there, would be 2 divided by pi. Nice. Well, to finish off today, we have 4 practice problems, and although I have worked out the solutions, I think you guys probably enjoy it a little bit more when you can hear me speaking them out loud as opposed to just reading through it. So what I'm going to do is have you guys take a shot at each one of these, and you can, try one, watch one, or try all 4 and then watch all 4, whatever sounds good to you. And I just tried to find a variety of practice problems, really from past AP exams, though I altered them a little bit, and I did make up the 4th problem. You should try to do these without a calculator too, and we can kind of see how this average value shows itself on the AP exam. So good luck, and then unpause me whenever you're ready. All right. Okay, picture a funnel of height 10 inches. So hopefully we've seen funnels before, right? Funnels kind of look like this. They have a little opening in the bottom, and then they're usually circular. Right, so here's my circle, and then there's this piece down at the bottom where things go out, right? So here's my funnel, and you might notice then that this funnel is actually made up of circles. Okay. And they're telling us at any height h, though this funnel in general is 10 inches tall, so we're going to show it out here so we don't get confused by what the 10 is. So this is a height of 10. They're giving us the radius, so they're saying at any height h, we have a formula for the radius of one of these little circles that makes up the funnel. And the radius is 1/10 5 plus 2h, where you can use any h value from 0 to 10. Find the average value of the radius of the funnel in inches. Okay, let's see what we can do. So the radius, average value, is going to be 1 over, what are our b and a here? Well, the only restrictions I see are restrictions on the height, so let's try to use the height. So we're going to use these restrictions on the height. 10 to 0, 0 to 10. If I'm using height in my formula, then I think everything in here should be in terms of h, which is actually useful because the formula for the radius is given in terms of h, right? 1/10 times 5 plus 2h. And then what do we end with? D what? Well, everything's in terms of h, so let's end with dh. Okay. Continue out here. 1/10 is on the outside. Actually, let's bring the other tenth out to join the first 1/10, and let's make it 1/100th. And then let's do the antiderivative of the inside with respect to h. Antiderivative of 5h, 2h, h squared from 0 to 10. All right, we're going to use a little arrow and jump over here, so 1/100th. And then we substitute in. 10 times 5 is 50, and then 10 squared is 100, minus, and then substituting in 0, I think is just going to give us 0 here. 1/100th times, this is 150, and simplifying, we get 15 over 10, or dividing by 5, I think we get 3 halves. Great. Nothing bad. The average value of the radius in this funnel is 3/2 inches. They told us everything was in inches. Cool. Let's look at another. Let f be a function defined by this crazy thingamajig. Find the average value over that interval. Well, this is kind of a weird one because we have a function that splits at 0. So if we're going to find the average value, what we're really going to do is we're going to use our average value theorem, and I'm going to need 2 lines here. I'm probably going to work all the way to the right and then jump back again. So just starting our average value theorem, 1 over b minus a times the integral from a to b of f of x dx. And so this is a 1/2 out front. But the issue is how we calculate this area, because this area needs to be split over 2 functions. One function is in charge from one function is in charge from -1 up until we get to 0, and then the other function is in charge from 0 to 1. So we're going to actually split this integral, and we'll do it like this, and we're going to say to find this total area, we're going to first find the area from, and I'm having trouble, there we go, from -1 to 0. Which function is in control less than 0? Oh, this one. 1 minus 2 cosine of pi x dx. Then we're going to find all the area from -1 to 0 first, and then we'll find the area from 0 to 1 of this function. Okay, so let's do some antiderivative stuff. Notice it is 1/2 out front. We don't redo the 1 over b minus a with the 2 different integrals, right? This is showing us the full length of the integral. Okay, so as we go through here, antiderivatives could be a little tricky, but nothing bad. 1, I think, becomes 1x. And then let's just kind of guess at this and make it work. So I see cosine, so let's keep the negative for now. So 2 sine of pi x. And then think about the derivative. The derivative of this, -2, will stay. Not bad. Sine turns to cosine. That's good. But then pi x will stay. It's on the inside, but it will be multiplied by the derivative of pi x, which would mean an extra times pi would pop out here. What would cancel out the pi? I think we can do divided by pi. Right? The derivative then would cancel out the division of pi right there. Nice. So then from -1 to 0 plus, and then this guy, I always start with the e first, and I think, okay, well, did I get it right? The derivative of e to the -4x would be, well, there'd be an extra -4 out front due to the derivative of -4, but I want it to be 8. -4 times what gets me 8? I think we need a -2 here. Those will multiply, give us the 8, and we're looking pretty good. All right, let's start plugging things in. So again, I promised you a nice little arrow over here. So 1/2 times, and then I'll switch to some big brackets here. If I substitute in 0, I'm going to get 0 minus, and then this is sine of 0, and sine of 0 is 0, I'm pretty sure. So that all becomes 0 as well. Cool. Minus, now we substitute in -1. So I get -1 times 1, which is -1. And then this becomes -1 pi. So -1 pi swings us back. It's actually coterminal with pi, and sine of pi is also 0. So that is a -0 here. There's the first one. Ah, pretty nice numbers, no trig functions. Woo, go us. Plus, now we plug in the upper limit here, so we get -2e to the -4th. That's with substituting in 1. And then minus the lower limit, which is going to be -2e to the 0th. And I think now we can start to clean this up a bit. So we have 1/2, still on the outside. This is 0, don't need to write that. Minus -1, so we get 1 here. Minus 2e to the -4th. And then this at the end, e to the 0th is 1. 1 times negative 2 is negative 2. Plus negative 2 is going to be a plus 2 here. So I'm looking at 3 minus 2e to the negative 4th over 2. 3 minus 2e to the negative 4th over 2. Now some people will ask, wait, how far do we have to simplify? Can we go further? Should we find a decimal? Well, to the decimal question, the answer is almost always no. If you can avoid writing infinite decimals, like e is transcendental, goes forever, you should always avoid writing the decimals. Where to stop, though? Well, it actually doesn't matter. You could have stopped here. That's the same as our answer. You could have stopped even here if you wanted, as gross as that is, right? The AP exam doesn't try to define what simplified is. They don't even ask you to simplify. They just want to make sure you got the right answer. And technically, all three of these are the right answer, but we'll talk more of that as we move through. Let's try another. All right, looks like pretty much the exact same thing. You should probably try to pause me and make sure you can work through this on your own, and then we will come together shortly. All right, I hope you found some success on this problem. I'm going to try and use 3 lines here. I might need more space, I'm not sure, but I'll start up above. If we're going to find the average value, it's 1 over 2 minus 0 times the integral from 0 to 2 of f of x dx. Of course, we're going to run into the same issue that we did before. We'll need 2 integrals here, so that average value, let's make sure I have enough room here, is going to be 1/2 times the integral from 0 to 1, and that's going to be the function x to the 1/2. I know it's square root of x, but I know I'll need the antiderivative, and I prefer that fractional exponent than anything else. And then we have the integral from 1 to 2, right, of x squared dx. So let's do some antiderivatives. Okay, antiderivative of x to the 1/2, we add 1, that's 3/2. But we'll cancel the 3/2, but a 2/3. 0 to 1, plus, and then our next one is 1/3 x cubed from 1 to 2. Looking not too bad. You can remember that x to the 3/2, and I can show this over here, is the same thing as x cubed to the 1/2, right? Half of 3. And we should know that the 1/2 power means the square root. So it's really the square root of x cubed. It turns out to matter much less in this problem because we're just substituting in 0, and any root of 0 is 0, and substituting in 1, and any root of 1 is 1. But it's always nice to remember. So as I go through here then, we continue this out. We still have the 1/2 out front, and now we start evaluating. We substitute in 1. 1 to the 3/2 is 1, but then there's a 2/3 still hanging out. Minus, then we substitute in 0, which is 0. Add in the next one. Now we substitute, and we get some kind of uglier numbers. 2 cubed is 8. 8 divided by 3 is 8/3. Minus, then we substitute in 1, which is 1/3. But you might notice very cleverly, I think, because I changed this problem and I made it have actually nicer answers. Those fractions aren't nice, but they kind of are, because 2 plus 8 is 10, minus 1 is 9. So this becomes 1/2 divided by 9/3. 9/3 is just 3, so I think we get a final answer of 3/2. Not bad with no calculator, huh? Okay, last but not least. The competition. Mr. Grant and Mr. Barr are given the equations f of x equals x cubed and f prime is 3x squared on the closed interval. They're asked to find the average value of f prime, and so they set up their work as follows. Mr. Grant does this weird thing. That seems bizarre. Mr. Barr, though, does what seems like we should do. So what's the correct answer? Well, let's work with Barr because that seems like the right thing to do. So we're looking for the average value of f prime. And so it seems like we should set it up like Mr. Barr did. Okay, so integral from 1 to 3 f prime of x dx. Quickly checking, the integral will find f of x, but then dividing by 3 minus 1 will bring it back down to f prime. So yeah, that seems pretty good. Let's actually work this out and find the answer here. 1/2, times the antiderivative of f prime is just f, so that's x cubed, isn't it? From 1 to 3, so it becomes 1/2, and then we do 3 cubed, which is 27, 1 cubed, which is 1. I'm looking at 26/2, which equals 13. Average value in this function, 13. Barr did great. Now, Mr. Grant wrote something that looks nothing like our average value theorem or formula that we've done so far. Let's at least see what Mr. Grant got as an answer, though, and then we can really just slam him and say, ha, you're wrong, crazy kid. So if we're going to work with this, this says f of 3, and f of 3 is going to be found by doing x cubed. So we have f of 3 minus f of 1 divided by 3 minus 1. So f of 3 means cube 3. F of 1 means cube 1, and then divide by 3 minus 1. This is 27 minus 1 over 3 minus... I'm looking at 26 over 2. I'm also looking at 13. So could Mr. Grant be right? Why is he right? Well, think about what Mr. Barr did down here and realize that we could certainly rewrite this. We could kind of combine this all together and say the integral from 1 to 3 of f prime of x dx divided by 3 minus 1. And you're like, well, why would you want to do that? But fundamental theorem says the antiderivative of f prime is f, right? F of x from 1 to 3. And then couldn't we rewrite this as f of 3 minus f of 1 divided by 3 minus 1? And isn't that what Mr. Grant wrote up here? Doesn't that look correct as well? And so really what we're doing here is this is our friendly mean value theorem for derivatives. This is the average rate of change of f. But if we're looking for the average rate of change of f, then this is kind of like the derivative of f, right? And this is finding something about f prime. In fact, it's finding f prime of c, which we've learned before is the same as the average value of f prime. So this gets a little bit tricky in that there are two different ways that you can set up to find the average value. The more typical way is this way, and it's going to find the average value of f prime. But don't forget that the mean value theorem is also finding the average value for f prime, just in a different format. So a little tricky, but you'll get to keep practicing. You'll be just fine with this. And hey, good news, you're done with topic 5. You're done with the tough unit here. So thank you so much for hanging out with me on this adventure. We'll be back a little bit later on after you guys do all your review and your test to hit up topic 6. We only have 2 topics left before you've covered all the content for the AP exam. And as promised, those last 2 are much shorter. So thank you again for your time, and I'm excited to see you back for topic 6.